Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to continue our lecture on chemical thermodynamics, and we've made it to the fifth objective, which is titled Gibbs free energy. Gibbs free energy is a state function that combines enthalpy, temperature, and entropy into a single equation, and this equation is a powerful tool to use to predict the spontaneity of a reaction. We have in this equation that the change in Gibbs free energy is equal to the change in enthalpy minus temperature multiplied by the change in entropy. Now, the Gibbs free energy change reflects the balance between the energy released or absorbed and the dispersal of energy. For a process to be spontaneous, delta G needs to be negative, meaning that the free energy of the products is lower than that of the reactants. In thermodynamics, if we see a term like delta G, delta H, or delta S without any subscripts, we generally assume it applies to the system. We can actually write it more explicitly like you see here. We're going to take this equation and we're going to manipulate it so we can better understand what delta G of the system tells us. We're first going to divide both sides by temperature. When we do that, we get the following equation. From here, we're going to multiply both sides by -1 to get this version of the equation. Now, I want to point out this term in particular. This term right here is equivalent to the change in entropy of the surroundings. If we replace this term with delta S of the surroundings, we now have on the right side of this equation, delta S of the surroundings plus delta S of the system. That is equivalent to the change in entropy of the universe. So ultimately, this version of the equation tells us that the negative change in Gibbs free energy of the system divided by temperature is equal to the change in entropy of the universe. This derivation is significant because it connects delta G directly to the total entropy change of the universe. In essence, the Gibbs free energy change of a system provides a direct measure of the overall entropy change for the universe. So when delta G of the system is negative, delta S of the universe is positive, indicating a spontaneous process that increases the entropy of the universe. That means that the sign of delta G tells us the spontaneity of a reaction. If delta G is negative, then the reaction is spontaneous. If delta G is positive, then the reaction is non-spontaneous. And if delta G is equal to 0, then the system is in equilibrium. Now, a helpful way to visualize Gibbs free energy changes is by looking at energy diagrams. When delta G is negative, so delta G less than 0, then what we have is an exergonic reaction. In an exergonic reaction, the energy of the products is lower than that of the reactants, and that indicates a release of free energy, which favors spontaneity. Now, what about when delta G is positive? So delta G is greater than 0. Then we're considering an endergonic reaction. In an endergonic reaction, the products have a higher free energy than the reactants, meaning that energy must be supplied for the reaction to proceed, so it's non-spontaneous. We can also predict spontaneity by analyzing the signs of delta H and delta S. This table helps summarize that. When delta H and delta S are both positive, then the reaction is spontaneous at high temperature because the T delta S term becomes large enough to make delta G negative. When delta H is positive and delta S is negative, then the reaction is non-spontaneous at all temperature because both terms contribute to making delta G positive. When delta H is negative and delta S is positive, then the reaction is spontaneous at all temperatures because both terms make delta G negative. And finally, when both delta H and delta S are negative, the reaction is spontaneous at low temperature because the negative T delta S term becomes less significant. Now, the trends in this table can be a lot to memorize, so let's play around with some numbers so we can better understand this table without exactly needing to memorize it. To begin, we're going to write our equation. Delta G is equal to delta H minus T delta S. We're going to work through the first line of this table where both delta H and delta S are positive. Let's assign some values. Let's pretend that delta H is equal to 100 joules and delta S is equal to 2 joules. If we plug this into our expression, we get that delta G is equal to 100 minus T multiplied by 2. In order for a reaction to be spontaneous, delta G needs to be negative. For this to be true, we need temperature to be a high temperature. In this scenario, temperature has to be greater than 50 Kelvin so that the TS term is large enough to be subtracted from 100 and give us a negative delta G. Let's say that temperature is 55. This would give us 100 minus 110, and that would give us a delta G that is equal to negative 10 joules. So this reaction would be spontaneous. Okay, so that's our first row in our table. Let's work on the second row of the table. In the second row of the table, we have a positive enthalpy and a negative entropy. So again, let's say that delta H is equal to 100 joules, but now let's say that delta S is equal to negative 2 joules. Let's go ahead and plug this into our equation. Delta G is equal to 100 minus T multiplied by negative 2. Now I want you to keep in mind that temperature here is in Kelvin. If it's in Kelvin, it can never be a negative number. That means that this term right here will be positive because we have negative T multiplied by negative 2. Two negatives make a positive, so this equation is 100 plus 2T. There is no value of temperature here that would give us a negative delta G. So when delta H is positive and delta S is negative, the reaction is non-spontaneous at all temperature. In our third scenario, we're going to consider that delta H is negative and delta S is positive. We're going to assign delta H a value of negative 100 joules, and we're going to assign delta S a value of 2 joules. Let's plug this into our equation. Delta G is equal to negative 100 minus T multiplied by 2. In this equation, we have a negative number, and then we're subtracting from that negative number. So that means at all temperatures, at all values of T, we're going to get a negative delta G, which means that for a negative delta H, positive delta S, the reaction is going to be spontaneous at all temperature. Now let's do our last and final scenario when delta H and delta S are both negative. we're going to assign delta H to be negative 100 and delta S to be negative 2. Our equation is now delta G is equal to negative 100 minus T multiplied by negative 2. Now this minus TS term is going to be positive 2T because we're multiplying two negatives, that gets us a positive. So our equation is negative 100 plus 2T. If we want delta G to be negative, then T needs to be a small value. Specifically for this problem, T needs to be less than 50 Kelvin. If T is 40, then we have negative 100 plus 80, and this will give us negative 20, which is a negative value for delta G, so the reaction is spontaneous. In short, when delta H and delta S are both negative, the reaction will be spontaneous when temperature is low. Wonderful. Now that we've worked through this, I want to discuss two ways to approach delta G. So two ways to think about Gibbs free energy. First, to reiterate, delta G serves as a measure of the spontaneity of a process. We've really drilled this up until this point. So if delta G is negative, then the process is spontaneous, and if it's positive, then the process is not spontaneous. The second way that you can interpret delta G is that delta G represents the maximum amount of useful work that can be obtained from a process at a constant temperature and pressure, and that can be written in this form. Delta G is equal to the maximum work. This equation tells us that Gibbs free energy change reflects the potential for a reaction to perform work. And with that, we've completed Objective 5, and we can now move into Objective 6. Objective 6 deals with calculations involving standard free energy change. There are tables of thermodynamic data that are widely available, and they enable us to determine the standard Gibbs free energy, standard enthalpy, and standard entropy for many reactions. These tables generally include the standard Gibbs free energy of formation, the standard enthalpy of formation, and standard entropy for different substances. Now, the subscript 0 that you see here, this is used to specify that all reactants and products are in their thermodynamic standard state. The conditions for standard state are the following. Each gas exerts a partial pressure of exactly 1 atmosphere. Each solid or liquid is in its pure form at exactly 1 atmosphere of pressure. Each solute in a solution has a concentration of exactly 1 molar, and finally the temperature is 25 degrees Celsius, which is equal to 298 Kelvin, unless otherwise specified. Using thermodynamic tables, we can determine the standard enthalpy change of a reaction, the standard free energy change of a reaction, and the standard entropy change of a reaction for a specific reaction in a manner that's really similar to Hess's law. And this is done simply by summing the enthalpies, the Gibbs free energies, and the entropies of formation for the products and reactants. The general formulas for these calculations are shown here, and what you notice is that they are very similar to each other. The only difference is one is for enthalpy, one is for Gibbs free energy, and one is for entropy. Let's discuss each formula to make sure that we understand it. Let's start with the standard enthalpy change for the reaction. The standard enthalpy change of a reaction is calculated by taking the sum of the standard enthalpies of formation for the products, each multiplied by their respective stoichiometric coefficients, and then subtracting it from the sum of the standard enthalpies of formation of the reactants, each also multiplied by their respective stoichiometric coefficients. Now, let's talk about standard Gibbs free energy change for the reaction. This is found by taking the sum of the standard Gibbs free energies of formation for the products, each multiplied by their respective stoichiometric coefficients, and then subtracting it from the sum of the standard Gibbs free energies of formation of the reactants, each also multiplied by their respective stoichiometric coefficients. I think you're catching on to the trend here, but alas, we will do the standard entropy change for the reaction. This is calculated by taking the sum of the standard entropies of the products, each multiplied by their respective stoichiometric coefficients, and then subtracting it from the sum of the standard entropies for the reactants, each also multiplied by their respective stoichiometric coefficients. So again, in each case, the calculation involves determining the total for the products and then subtracting the total for the reactants using standard values for enthalpy, Gibbs free energy, or entropy. Let's go ahead and jump into a practice problem. This problem wants us to look at the complete combustion of 1 mole of methanol at 298 Kelvin and determine the following values. Here we're given the balanced chemical equation for the combustion of methanol, and we're given a table full of values. Here we're given the standard enthalpies of formation, the standard Gibbs free energies of formation, and the standard entropy for methanol, carbon dioxide, and water. To start solving this problem, we notice that the balanced chemical equation has a coefficient of 2 in front of methanol. Since this problem specifies the combustion of just 1 mole of methanol, we can simplify the equation by dividing every term by 2. This gives us the following chemical equation. We'll be looking at this chemical equation to obtain the coefficients we need to solve for these values. Now, let's start with determining the standard enthalpy change of reaction. To do this, we're going to take the sum of the standard enthalpies of formation of the products, each multiplied by their respective stoichiometric coefficients, and subtract it from the sum of the standard enthalpies of formation of the reactants, each also multiplied by their respective stoichiometric coefficients. So for the products, this is going to be carbon dioxide and water. Carbon dioxide has a coefficient of 1, water has a coefficient of 2. We can go ahead and get these values from our table and plug them in. Our reactants are methanol and oxygen gas. The coefficient associated with methanol is 1, and for oxygen gas, it's 3 divided by 2. We can go ahead and get the standard enthalpy of formation for methanol from the table and plug that in. For oxygen gas, since this is in its standard elemental form, the enthalpy of formation is just going to be 0. So now we have our values plugged into this equation. Calculating this on a calculator, we get that the standard enthalpy change for the reaction is equal to negative 726.4 kilojoules. We can then go ahead and do the same thing for the standard Gibbs free energy change for the reaction, getting our values for the standard Gibbs free energies of formation from the table and plugging them in. And what we get is that the standard Gibbs free energy change for the reaction is equal to negative 702.3 kilojoules. Finally, we can work on the standard entropy change for the reaction. Again, the calculation is very similar. It involves determining the total for the products and then subtracting the total for the reactants. And what we get for the standard entropy change for this reaction is negative 81 joules per Kelvin. And with that, we've solved this problem, and we can now move into our 7th objective. In this objective, we're going to be moving away from calculations involving standard conditions into calculations involving non-standard conditions. Actually, most chemical reactions occur under non-standard conditions, meaning that the concentrations, pressures, or temperatures differ from the defined standard states. To account for this, we use an adjusted form of the Gibbs free energy equation that relates the standard free energy change to the free energy change under these non-standard conditions. The equation connecting these two forms of free energy is given right here. Delta G is the free energy change under non-standard conditions. Delta G naught is the standard free energy change. R is the ideal gas constant, and it is equal to 8.314 joules per mole times Kelvin. T is temperature in Kelvin, and Q is the reaction quotient, which reflects the ratio of the concentrations or partial pressures of the products to the reactants at any given moment during the reaction. This equation shows us that delta G depends on both the intrinsic properties of the reaction, as given by delta G naught, and the current conditions of the reaction through Q. When Q is equal to 1, this natural logarithm term disappears, and what we have left is that delta G is equal to delta G naught, indicating standard conditions. However, when Q does not equal 1, then delta G will deviate from delta G naught, reflecting the actual progress and conditions of the reaction. By understanding and applying this equation, we can determine the free energy change at any point in a reaction, and that's going to allow us to predict how far a reaction is from equilibrium and in which direction it might proceed. If delta G is negative, then the reaction will move forward spontaneously towards equilibrium. If delta G is positive, the reaction is non-spontaneous in the forward direction under those conditions. Let's make sense of this by tackling a practice problem. This problem wants us to consider this reaction. We have 1 mole of nitrogen gas reacting with 3 moles of hydrogen gas to give us 2 moles of ammonia gas. And here we're given delta G naught, which is the standard free energy change. We're asked what is the value of delta G at 298 Kelvin when the partial pressure of nitrogen gas is 1 atmosphere, the partial pressure of hydrogen gas is also 1 atmosphere, and the partial pressure of ammonia gas is 1 atmosphere. To solve this problem, we're going to be using our equation right here. The first thing we want to calculate actually is Q. So let's go ahead and do that. Q is going to be the partial pressure of the products raised to their respective stoichiometric coefficients divided by the partial pressures of the reactants raised to their respective stoichiometric coefficients. So we have the following expression for Q. Now we're given the partial pressure for each of these gases, so we can go ahead and plug them in. It's just 1 squared divided by 1 multiplied by 1 cubed. Very easy calculation. This gets us 1. Now this indicates to us that we're actually under standard conditions. So in the case that you've forgotten what standard conditions are, Just doing this calculation is going to indicate that to you. And that is because Q is equal to 1. The natural logarithm of 1 is equal to 0. So that means we lose this whole term right here. What we're left with is that delta G, the free energy change under non-standard conditions, that's equal to delta G naught, which is the standard free energy change. And we're given that value, it's equal to negative 32.8 kilojoules. So in this problem, we're actually under standard conditions, but we went ahead and we worked through this problem nevertheless, and it indicated to us that for this specific scenario, delta G is equal to delta G naught, and the final answer is negative 32.8 kilojoules. With that, we move into objective 8, called free energy and equilibrium. Now that we understand how Gibbs free energy changes under non-standard conditions, let's explore the connection between free energy and equilibrium. The reason we want to do this is because this relationship is essential for understanding the direction in which a reaction will proceed under given conditions. We're going to start with writing our equation for non-standard conditions. Delta G equals delta G naught plus RT natural log Q. When a system reaches equilibrium, there is no further net change in the concentrations of reactants and products. And that means that the system has reached a stable state. At equilibrium, Q is equal to K, where K is the equilibrium constant. And in this scenario, delta G is also going to be equal to 0 because there is no driving force for the reaction to proceed in either direction since we're at equilibrium. So when we substitute these values in, we get that 0 is equal to delta G naught plus RT natural log K. We're going to rearrange this equation, so we're going to subtract RT natural log K from both sides, and what we get is the following expression. Delta G naught is equal to negative RT natural logarithm of K. This equation directly relates the standard free energy change to the equilibrium constant. It tells us that delta G naught and K are linked by the temperature and the reaction's equilibrium position. This relationship provides valuable insight into the spontaneity of a reaction under standard conditions. When K is greater than 1, then delta G naught is less than 0, and that indicates that the forward reaction is spontaneous under standard conditions because the equilibrium position favors the products. If K is less than 0 and delta G naught is greater than 0, this indicates that the forward reaction is not spontaneous under standard conditions and the equilibrium position favors the reactants. When K is equal to 1 and delta G naught is equal to 0, this indicates that the system is at equilibrium under standard conditions, so there is no net favoring of reactants or products. In addition to standard conditions, we can predict the direction of a reaction by comparing Q and K. If Q is less than K, then the reaction will proceed in the forward direction to reach equilibrium because more products need to be formed. If Q is less than K, then the reaction will proceed in the reverse direction because there's too many products relative to reactants. And if Q is equal to K, then the system is at equilibrium under standard conditions. So there is going to be no net change in the concentrations of reactants and products. Keeping this in mind, let's jump into a practice problem. This problem says, what is the equilibrium constant for the synthesis of ammonia at 25 degrees Celsius? We're given the equation. We have 1 mole of nitrogen gas reacting with 3 moles of hydrogen gas to give us 2 moles of ammonia gas. We're also given delta G naught. It's equal to negative 32.8 kilojoules at 25 degrees Celsius. Now, the relationship between delta G naught and K, that's given by this equation right here. Our goal is to calculate the equilibrium constant, so we want to isolate this natural log K variable, and we can do this by dividing both sides by negative RT. When we do this, we get the following equation. Now we have all three of these values. We are given delta G naught, R is a constant, and we're also given temperature. But here's the thing, we need to watch the units. Temperature is expressed using the Kelvin scale. Delta G naught is given to us as negative 32.8 kilojoules per mole. And R is usually given in units of joules per mole times Kelvin. What we want to do is we want to modify the units for either the ideal gas constant or delta G naught to make sure that they match. What we're going to do is modify delta G naught from units of kilojoule to units of joules. Negative 32.8 kilojoules is equal to negative 32,800 joules. So let's go ahead and plug that in. We have negative 32,800 joules per mole. This is divided by our ideal gas constant, which is equal to 8.314 joules per mole times Kelvin. And our temperature is 298 Kelvin. 298 Kelvin is equal to 25 degrees Celsius. Now here, joules cancel out, moles cancel out, K's cancel out. This is perfect because what are we calculating? The natural log of K. When we plug the right side of our equation in the calculator, we get that this is equal to 13.24. Now we want to solve just for K, so we want to get rid of this natural logarithm on the left side. To do that, we have to do e raised to the right side. Again, we can plug this into our calculator, and what we get is that K is equal to 5.62 times 10 to the 5th power. And there we have it. We've answered this problem. We've figured out the equilibrium constant for the synthesis of ammonia at 25 degrees Celsius. Now we can move into our last and final objective. In our study of Gibbs free energy and equilibrium, an important consideration is how temperature affects both delta G and the equilibrium constant. The values of these quantities are not fixed. They depend on the temperature. So understanding this relationship allows us to predict how reactions shift under different thermal conditions. We're going to start with writing our two essential equations. Here we have the relationship between delta G naught and K. And here we have our good old Gibbs free energy equation. Since both equations describe delta G naught, we can set them equal to each other. So now we have negative RT, natural log K, is equal to delta H minus T delta S. And this is in standard conditions. What we're going to do next is divide both sides by negative RT. Now we have an equation that defines natural log K. This is equal to negative delta H divided by R multiplied by 1 over T plus delta S divided by R. This equation resembles the form of a straight line. Y equals mx plus b. Y is natural log K. The slope m is equal to negative delta H divided by R. And x is going to be equal to 1 over T. And then the y-intercept b, that is equal to delta S divided by R. This linear relationship tells us that by plotting natural log K against 1 over T, we're going to get a straight line with a slope related to the enthalpy change and the intercept related to the entropy change. Using this equation, if we know the equilibrium constant K at a particular temperature T, we can predict what K would be at a different temperature, provided we know delta H. To calculate K at two different temperatures, we're going to use the following derived equation. This one right here. To get this, we've taken our expression of natural log K for temperature 1 and for temperature 2, and we have essentially done the natural log of K2 divided by K1, and we obtain the following relationship. We're not going to get into too many details about this. You can work this out on your own, but this equation is very important to know and understand. In this equation, K1 is the equilibrium constant at the initial temperature T1. K2 is the equilibrium constant at the new temperature T2. Delta H is the standard enthalpy change, hence why it has this little 0 degrees, delta H naught, and it's divided by R, which is the ideal gas constant, and that's all multiplied by 1 over T2 minus 1 over T1. T2 is the new temperature, T1 is the initial temperature. This equation allows us to calculate the change in K as the temperature changes, which gives us insight into how temperature shifts can alter the position of equilibrium. So for example, if the reaction is exothermic, which means that delta H naught is less than 0, then increasing the temperature will decrease K, and that favors the reactants. If the reaction is endothermic, which means delta H naught is greater than 0, then when we increase temperature, we're going to also increase K, and that favors the products. Now with that, let's go ahead and jump into a practice problem so we understand how to use these equations. This problem says the equilibrium constant Kp for the reaction below is 5.6 times 10 to the 5 at 25 degrees Celsius. What is the equilibrium constant for this reaction at 150 degrees Celsius? Our reaction is of nitrogen and hydrogen gas together to form ammonia gas. We're given that delta H naught is equal to negative 91.8 kilojoules. To solve this problem, we're going to be using this equation. We're given K1, we're given T1 and T2, we're given delta H naught, and we know R because R is a constant. So let's go ahead and plug in the variables we know and begin to solve. Our ultimate goal is to calculate K2. So here we have the natural log of K2 divided by K1, which is 5.6 times 10 to the 5. This is equal to negative delta H naught. Now this is in units of kilojoules. We're going to convert that to joules so it matches the units for the ideal gas constant. It is equal to 91,800 joules per mole, and it's divided by R, which is equal to 8.314 joules per mole times Kelvin. Then this is multiplied by 1 over T2. T2 is 150 degrees Celsius. We want to convert that to Kelvin by adding 273. We get 423 Kelvin minus 1 over T1. T1 is 25 degrees Celsius. This is equal to 298 Kelvin. Now let's calculate everything on the right side of this expression. When we do that, we get negative 10.94. Now to the left side, I'm going to rewrite this. This is equivalent to natural log K2, the numerator, minus the natural log of the denominator. So this is natural log K2 minus natural log 5.6 times 10 to the 5. We can go ahead and add the natural log of 5.6 times 10 to the 5 to both sides so that we now have natural log K2 is equal to, if we plug this into a calculator, is equal to 2.29. Now we just want to solve for K2, so we want to get rid of this natural log. To do that, K2 is going to be equal to E raised to whatever's on the right side. So E to 2.29. If we plug this into a calculator, we're going to get 9.9. So K2, the equilibrium constant at 150 degrees Celsius for this reaction, is equal to 9.9. And with that, we've covered everything we needed to for this chapter. I hope that this was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.